Should I start?
Yeah, it's my pleasure to introduce the next speaker, Letterio Gatto, and he will speak about generalized Wronskians, Schubert calculus, and integrals on the Sato universal Grassmann manifold. Okay, you can.
Thank you very much. First of all, I want to express my deepest feeling of gratitude to the organizers to have let me be part of this nice fest, more than deserved fest in honor of Claudio, which I put in the list of my best friends in the academy and out of the academy. Secondly, as I said, unfortunately, I had not much time to prepare properly the slides. I have put some 3 keywords. Let me see. Generalized Wronskian, Schubert calculus, integrals of the universal Grassmann manifolds. As a matter of fact, the last part is the motivation who led me to study the first 2 items. I am not sure I will be able to say, according to the time, to say something about this last subject. And I have not been able, I had no time to write the proof of the unique result I will state, but I think I can do on the spot during the talk. I mean, when I will do live. Okay, but it's not ready on the slides. So this is, I mean, the wishing first slide. And then the aim of this talk is about some rather classical subject, the intersection theorem Grassmann variety, which is very well known. But the aim of this talk is to try to understand if is there any relationship between what I will define for you as being generalized Wronskians, Schubert calculus, in particular with the degree of Schubert varieties, and Schubert calculus, the intersection theory on the Grassmann variety is the very first example, is the prototype, is the father or the mother of all the possible intersection theories, and the integral on the Sato universal Grassmann manifold, by which I intend a suitable inductive limit of nested Grassmannians. I don't want to be very technical here, but this object, as I am thinking to, is defined in a paper by Sato in a volume of a conference in 1982, and also just a moment. Sorry, it's night the time at the 4:30. Sorry. Scusate. So then also another rigorous construction can be found also in a recent paper by, or relatively recent paper by Ivan Penkov and collaborator, where this universal infinite dimensional Grassmannian is constructed via some suitable inductive limit, and I will not be more detailed in this case. So the minimal framework to let generalized Wronskians come to life is to consider an algebra over a Q algebra R. So you have A, which is an R algebra, and R itself a Q algebra, equipped with an R derivation dA to A. But since I want to show how this subject is very much related with our very first mathematical experiences, I want to forget this general framework and I want to stick to a very familiar one, namely the case in which I consider an open set of the real line and and R tuples of C infinity functions defined on the open set U. And our derivation is just the derivative with respect to the usual x coordinates. And the iterated of the derivation, the usual derivative with respect to x, I denote by d to the power j. And when applied to the R tuples, it means just considering the derivatives of each component of the R tuples. This is rather simple. And if lambda is a partition, that is a sequence of integers, non-increasing, of positive integers, which are all zeros, but finitely many, we can associate what I defined in some papers related with the loss isobias points in the moduli space. Of course, I defined this, I called this natural object generalized Wronskians, which means considering the first column. Notice that I'm changing a bit the usual notation. I put the R tuple in column, and then I consider the derivative of order R minus 1 plus lambda 1 of the first column, then the derivative of order R minus 2 plus lambda 2 of the column of the R tuples, and so on. This is the usual Wronskian. I mean, then not to be, for simplicity, we denote in form of an exterior power, because you see, if we consider this exterior power, we land in the top exterior power of the direct sum of R copy of the C infinity U, and we land in C infinity U. So as a matter of fact, it's a C infinity function, and if lambda is equal to 0, you get the usual notion of Wronskians. So something that is very natural. Instead of considering the first column, the derivative of the column, the second derivatives, you prescribe the order of derivative you want to consider, and this order of derivation or derivatives you take for the elements of the R tuples is prescribed by assigning this partition. And we recall this fact that if the Wronskian of the R tuple is not 0, then F0, F1 up to Fr minus 1 are linearly independent, while we know already that the converse is not true. So these are the basic objects I want to discuss. And yeah, I give a sketch of the history of subject, just very sketchy because I had no time to be more precise. But the connection of Wronskians with Schubert calculus have been already considered in literature. Studied, for instance, to study problems of real algebraic geometry by Eremenko and Gabrielov, who studied the degree of the Wronski map. I thought I had the yes, this is the so-called Wronski map. You take, this Cn, you should think this Cn as a Cx modulo xn xn. So these are the polynomials of degree of not bigger than n minus 1. Is isomorphic to Cn, as if you consider the derivative with respect to the indeterminate x, the formal derivative, and then you can construct some Wronski map, which associated to an R tuples of polynomial, it's Wronskian, and say, this is studied by Eremenko and Gabrielov in the real context. Then there are other papers by Shapiro and Shapiro who studied linear OD connected with the Sturm theory and studied their Wronskians and use some real Schubert calculus as well. Then in 2003, appear some papers by Scherbak and Varchenko studying so-called generating functions of Wronskian maps in connection with Bethe and Satz, and in spite they are more interested in the real situation, then Scherbak is also able to find a new formula for intersection of spatial Schubert cycles in the Grassmannian of two planes using representation theory of SL2C. This is a rough story. And now, this is the point in which I try to begin officially the talk, and I want to discuss a bit about partitions that we know, but I define again. These are sequence with finite support, non-increasing sequence of non-negative integers with finite support. And each partition is a partition of an integer. For instance, if I take the integer 3, I have a 3 partition of this integer 3, 2, 1. We omit the 0 terms, and 1, 1, 1. Okay? And the length of the partitions is a partition as a finite support is the number of elements of the support, the number of non-zero terms. And we denote by PR, here I see, I move the face of Marco. And
it's
PR,
okay, of course.
Yeah. And PR is the set of partition whose length does not exceed R. Now I want to consider an important vector space. I mean, it's important for me, I don't claim for the audience, which is the vector space generated by all the partition over the rational. The rational has to do because I want to study the cohomology of Grassmannian with rational coefficients. So it means any element of this vector space is a finite linear combination of... Yes? Yes?
Pour baisser le son, là, pour baisser le son.
It's okay. Are you hearing me?
Yeah, there is an open microphone,
okay.
But now I think it's closed.
So what I was saying is that an element of this vector space is just a finite linear combination of partition with the rational coefficients. And this vector space, which for me has a very intrinsic meaning, has two possible can be denoted in two ways. I call these the fermionic notation. But this vector space admits also bosonic notation. And the way to go from B to F0 is what I call the boson-fermion correspondence. I must explain you what is F0, but and also this space Q to the power P is isomorphic to the cohomology of the universal Grassmann manifold, because the universal Grassmann manifold comes endowed with the topology, so it makes sense to consider its cohomology. And this B, we will see in next slide. Anyway, we have then these several maps. We have an isomorphism to H star UGM and H lower star UGM. This would be in a sense the cohomology, and this would be in a sense the homology. And now I show you exactly how can I associate to a given partition an element of those spaces I claim the vector space generated by partition is related to. So first of all, if I take any partition, let's say, since a partition has a length, I take stick to the case in which the partition has length at most R, I can associate something which is very well known. B is the polynomial ring. If you don't like the rational because you are used with the complex number, you just tensor, but I don't need the complex. And then I limit myself to consider, I bound myself to consider the rational coefficients. And then S lambda X, even if I don't give you a formal definition, is something called a sure polynomial, is a polynomial in X1, X2, X3, in infinitely many indeterminates. Of course, once you fix lambda in the polynomial, only finitely many indeterminates will occur. But if you let the lambda varying over all the partition, then you see that, all the partition, then the S lambda X form a Q basis. So it's a Q basis of the polynomial ring in infinitely many indeterminates. The other object we can associate to a partition is a Schubert variety, which is a sub-variety, projective sub-variety of the Grassmannian. Which Grassmannian? I write this. The partition is of length at most R, and then I think into a Grassmannian GRN. Which N? I don't mind, provided that N is bigger than R. And this is also written in Fulton books, precisely in that chapter, I think, 14, where the author gives an account of the classical Schubert calculus and says, for the expression, the Schubert variety defined as I'm going to define, you see that I put the partition I put as upper index, not lower index, because these Schubert varieties that I'm going to describe better for you now is indexed by dimension and not codimension. The sum of the parts is the dimension. The dimension of these Schubert varieties is the weight of the partition. I will be more precise in a while. And to lambda, you can associate an element of F0. I'm not going to give you a precise, rigorous definition, but for the time being, you can think just as a formal way to write an infinite wedge power. When a wedge power, you see, I put in evidence, let's say, initial part which involves the parts of the partitions, wedge X minus R in parentheses, which means this guy. You say, what is X? Is because I'm considering this vector space. F0 is contained in an infinite, well, I should be more precise, infinite over 2, Qx minus 1 x. I mean, the vector space of Laurent polynomials. Let's see better the isomorphism as a vector space, as a Q vector space between Qp and H lower star UGM. What is a UGM? You want to take a point in UGM. This is clear from both the paper of Sato I cite for you is in the volume Baudoin 1982. Don't ask me to remember the name. I had no time to inform me better, to be more precise. But in any case, when you take a point of the universal Grassmann manifold, indeed, what you are doing is taking a point in a Grassmannian GRN with n big enough. And then also H star UGM, since since H star is covariant with respect to taking inductive limit, it means that you are taking an homology class in a Grassmannian GRN with n big enough. Then, if you consider the partition, you can associate to the partition a flag of subspace of Cn and any n bigger than R. And well, there should be a data. Oh, there is not. I am not explaining. Ah, yes, yeah, here. You see, such that the dimension of Fi is a vector subspace is I plus lambda R minus I. And then you have a Schubert variety. You don't need to catch the definition now, because clearly you have to think a little bit, but this gives you a projective subvariety with the Grassmannian of dimension equal to the weight of the partition, and you call omega upper lambda, superscript lambda, you call the homology class in degree to the weight of lambda of the Grassmannian, and any n
bigger.
Yes, yes, and I want to just to point out that the homology of the, well, here I think I wanted to write the cohomology, but I think this remark I will do better in the, yeah, no, this is contained here, the lower star. Okay. And this is a ring I called BRN, but it's not that relevant at the moment. And this omega lambda, all these lambda should be superscript. Sorry. Well, they can express in terms of polynomials in the Chern class of the universal quotient bundle of the Grassmannian, a Grassmannian GRN. And there is also what is called the Pieri formula. If you call the sigma I, the I Chern class of the universal quotient, then there is this Pieri formula which says sigma I is sigma I cap, means you are cutting with a linear subspace of codimension I, and you get the sum of some Schubert variety with dimension which must be lower of I mean, this should be I less, I mean, because the dimension, you can always realize the intersection in a transversal way, and in fact this is the condition which grants you that you are landing in the right dimension. But still, again, I don't want you feel familiar with what I'm saying. I'm just giving now an idea of how can I associate to a partition an element of the space. This is an element of F0. Sorry, this I already wrote, but I already written, sorry. And yeah, and the isomorphism between QP and the polynomial ring in infinitely many indeterminates. You see, I'm repeating myself. I associate to lambda the sure polynomials associated to lambda, where I am giving you this definition, the definition of S lambda X, underlined X, which is a sequence of infinite indeterminates, is given by this equality where PIUR means U1 to the I plus UR to the I, where U1, U2, UR are other formal variables. This is very classical. You can see in the McDonald book, for instance. But it's just to say you that these, when you are get used to them, these Schubert, these Schur polynomials are easily computable. And for instance, if I would write, for instance, S2 is x1 squared 2 plus x2, x3, S3 would be x1 3 over 3 factorial plus x1 x2 plus x3. And if you do two partition, you just do compute some determinants. Okay, I'm not asking you to get this formula at this very moment. Anyway, this is a remark. The remark is that if you restrict to the partition whose Young diagram is contained in R times n minus R rectangle, okay, then this isomorphism we saw before, the isomorphism with, I mean, the fermionic description would be just passing to the exterior power, while the bosonic description would be considering the cohomology ring of the Grassmannian, and then what we called before the boson-fermion correspondence is nothing but the Poincaré duality. But what I'm more interested in is the isomorphism as a Q vector space between Q to the PR, so linear combination of partition of length at most R, with what I call the Wronskian vector space, which is this vector space freely generated by the generalized Wronskian, where here I'm recalling for you the definition of generalized Wronskian. So it is a Wronskian where you use, you prescribe the order of derivative at each column. Proposition. Suppose that the Wronskian, the generalized Wronskian associated to the partition 0 is not 0. Then any generalized Wronskian is a multiple of the Wronskian. And the coefficient is a differentiable function. I call this differentiable function G lambda to remember the name of Giambelli. In a sense, it's a kind of Giambelli formula. But then we have another property that I'm sure will not surprise you at all, which says this. If you take the nth derivatives of the Wronskians, remember, the usual derivatives satisfy the Leibniz rule with respect to the multiplication, ordinary multiplication of functions. But precisely that Leibniz rule says that D satisfies also the Leibniz rule with respect to the wedge product you are using to express the Wronskian. You think a little bit about just taking the definition of the determinant using the substitution, the sum over all the substitution over n elements, and you see that taking the derivative of a Wronskian of f, taking the derivative of this, it means applying the Leibniz rule with respect to the wedge product. And what I was saying is that...
Sorry, Letterio. Sorry,
yes.
but in the last formula, you are deriving the Wronskian, which was defined in the first line
yes.
of this slide. Okay, so it's this calligraphic W.
Yeah.
Okay,
yeah.
okay, thank you.
No, the calligraphic is the vector space. Sorry.
Yeah, no, right. So
generated.
which kind of Wronskian you are?
The Wronskian is the usual Wronskian. You take the usual Wronskian,
W0.
the one we learned when we were
Zero.
Yeah.
It was zero.
Okay, now you added the
W0.
zero.
Yes,
okay,
I forgot the zero. Then you take the end derivatives, and you discover that it is a linear combination of generalized Wronskian with some coefficients, the sum over all the partitions of the integers n. Okay, provided that over all the partition the integer n, but since we are in the case of an R tuple of function, the length must be smaller or equal than R. And this omega lambda, in principle, may be rational, but indeed are integers. Okay. The proof, I wrote this proof, but it's stupid proof. The proof of the first, saying that all the generalized Wronskians are multiple Wronskians, depends on the fact that if the Wronskian W0F is different from 0, then our R tuples of function, meaning each entries of our R tuples of function, is a linear combination, is a solution of this linear ODE. Linear ODE with not constant coefficients. The coefficients are not constant. So since you have this linear equation, this F satisfied this linear ODE, you see that any derivative of order J of F can be expressed as a linear combination of, the span is over C infinity R of F dF dr minus 1F. And then it's clearly, by using usual properties of determinants, you find that A. To do B is a consequence of the fact that this D is an R derivation of this exterior power. And if you do a couple of experiments, you convince yourself easily that B is not even a theorem. This is just a remark. In fact, it's a proposition. Okay, let's go back some step backwards, and let's go back to Schubert varieties and consider for each partition PR, we denote the integral, the degree of the Schubert variety by omega lambda, which is what? You take the partition lambda, you take its weight, which is an integer, say let's m, and then you, but this is the dimension of the, okay, this is 0. This is the hyperplane class, sigma 1, it is a hyperplane class in the Plucker embedding of the Grassmannian. I'm sorry, this is, yeah. This is a Schubert variety of dimension lambda. You cap with the hyperplane section the weight of lambda times, and you get what is called the degree. This is a classical definition. You can find in Fulton book, and here is the formula. This is the formula. I wanted to compute for you omega 2,2 here. Omega 2,2 gives you, I checked the formula, you put instead of lambda 1, 2, and lambda 2 equal to, you find 2, which is the degree of the Grassmannian G24. Or if you want the number of line intersecting 4 others in general position in the projective space. This is the formula, which you can find in the Fulton book, where you read that it should date back to Schubert, and is proved in the book of Hodge-Pidio with many combinatorial work. Here is again the formula, and Fulton says, look, that this degree does not depend on the Grassmannian, where you are considering the Schubert varieties, but only on the partition. In a sense, what Fulton was showing us in that part of the book is the first example of what I call Schubert calculus on the fermionic Fock space, because he is working indeed on the infinite Grassmannian. I cannot be more precise here. Yes, I gave you an example, but I want to remind you that another way to compute the degree of a Schubert varieties is to consider a combinatorial formula, say to be the Hooke length formula. And you find the definition of the Hooke length of a box of a Young diagram in the book of Fulton. Just I want just to cite, to observe that there are many ways to compute degree of Schubert varieties. But this formula is a bit involved, you know, even with the Hooke length formula, is not very conceptual, because it's very combinatorial. In fact, in books of combinatorics, you can find this Hooke length formula, but there is no, it is not claimed any relationship with the degree of a Schubert variety. So if you want to compute omega 4, 3, 1, you take Fulton book, you say this is lambda 1, this is lambda 2, this is lambda 3, and so on. Now, I want to get back to Wronskian. Take any endomorphism of the C infinity, the vector space of C infinity functions, and define delta phi as being the unique derivation of this exterior algebra, such that when you restrict it to the first degree, is just the evaluation of phi. Okay, so it means that if you have delta phi f wedge g, this is phi f wedge g plus f wedge phi g. This it means you have this derivation, and then you can define a dz, a formal power series whose coefficients I call di as being the exponential of this expression. Okay, then we have the following. If you are not very used with the Schubert calculus, this formula don't say you many things, but the first part says that this di, precisely the di I defined with this expression, which occurs also in the theory, in the representation theory of the Heisenberg algebra, boson fermion correspondence. This is a part of the vertex operator, but the di, which is not d1 to the power I, is di w lambda is equal to the sum of generalized Wronskian, where the sum is over all the mu satisfying this. Okay. This is a technical condition. It's the Pieri formula. And then there is also Giambelli's formula. Giambelli's, you remember, I said you, oh, look, every generalized Wronskian is a multiple of the Wronskian, but the coefficients is a function. But if you use those differential operators, each di defined this way is in its rigorous sense a differential operator of order I of the exterior algebra, according to classical definition. And then we have a determinantal expression. So this delta lambda dz is a determinant involving those di's I defined for you. There was a sequence, d0, which is the identity, d1, which is the usual derivative, d2, d subscript 2, d subscript 3, and so on. And you have a determinant, which is not a function, it's an operator, but an operator constructed by means of the determinants of some operators. And then I claim that delta lambda f, yes, is a multiple of delta 0 f, and this delta 0 f to which you apply that determinant. And notice that I made no hypothesis on the R tuple of functions. The unique things I wanted is that they were differentiable of C infinity class. And then we have the main theorem. You didn't complain that I called omega lambda both the coefficients. You remember that I wrote for you that the dn w 0 is the sum omega lambda f partition of n, but then I also called for you omega lambda the degree of the Schubert varieties, and this is the main result I wanted to declare to you. I don't know if this is known in literature. It seems to me very fundamental, but the fact that if you take a Wronskian and you differentiate it as many times as you want, you get a linear combination of generalized Wronskians whose coefficients are precisely the degree of the Schubert varieties. Then at this point, there is augury, but I can go on if you want to give you an idea of the proof. If maybe I give you already because you are shy. Because you are shy.
Yeah.
Okay.
You have
20. Otherwise,
okay.
I can ask a question. Please, could you please give me a proof?
Okay.
Yeah.
Okay. So then this is the question. So the idea of the proof is the following. Consider this. You see, if you consider the homology of the Grassmannian, you know very well that this homology is generated by the class of Schubert varieties where the lambda are in where this lambda R partition contains in R times n minus R rectangle. But since we don't mind about the n, everything can be made more precise, but we don't mind about the n, we can think this object exists. You find also in the book of Bott and 2, this is the sum of Q omega lambda B in PR. Now, what you have is that if you take omega lambda, okay, we have now a map, a vector space map to the ring B in infinitely many indeterminates. Okay, it's just a vector space map. What does this map? Here I want to use lambda parameterized by dimension. Omega lambda, you associate the sure polynomials associated to the partition lambda in the indeterminates X. Now, you consider the Chern polynomial CTQ in this Grassmannian, and you can define the quotient in the quotient bundle. You can consider as approximation if you want, but the main point is that the CTQ capped with the sigma lambda, let's call this isomorphism by iota. So iota of this must give me a polynomial here. And the polynomial it gives me is precisely this. Not a polynomial, sorry, it's a formal power series, and it's precisely this. This is very interesting. It appears the 1 over sorry. Ti over I dxi s lambda x. And the point, so this is, we have this exponential, so it means that if I want to compute that cap product, it's enough to use a usual differential calculus. And that formula says this is published, I mean, I posted this in archive. I wanted to replace it with the update version, but I had no time. Archive Gatto, if you want to see the details of this result, Gatto, we are 2021. D over dxi over s lambda x is equal to the sum of s mu x, where mu satisfies that same condition we saw for the Wronskian and for the Schubert, for the degree of Schubert varieties. And then, so this means that since look that S lambda x, if you work in finite dimension, S lambda x is the way to express the class of a Schubert varieties. This is a class of Schubert varieties in the Grassmannian. And this is the idea of the proof. I mean, you just compare the formal properties. Since d over dxi satisfies the same property as di satisfy when evaluated against the Wronskian, then you have the conclusion. Or if you want, you read my papers of the last 10 years where I treat, where I phrase Schubert calculus in this way. You take the exterior algebra of a vector space of dimension n, wedge Vn T, and you consider the map, let's call this Z, dz, and dz u wedge V is equal to dz u wedge dzv. And then it turns out that this dz that I consider my previous papers is nothing but this vertex-like operator. And if you want to do some speculation, some philosophy, the point is that if you want to do Schubert calculus, you consider B, Q, X1, X2, and so on. Then you consider the Weil algebra of B, which means the algebra generated by multiplication by Xi and the derivative with respect to Xj. And each formal property you find of this Weil algebra with acting on B is precisely a formula of Schubert calculus, which means that each formula in Schubert calculus can be written as the action of these operators on this ring B, and also that you can find many more properties because you have here much freedom, and everything is reduced purely in in differential calculus. And these xi are very important because I want to recall you before ending my talk that if you consider the cohomology ring of the Grassmannian, you have three ways to write its presentation. One, the classical one, is putting the Chern class of the tautological bundle, and then quotienting with respect to the relation. This is the quotient. And another is writing by using the Chern classes of the quotient, n minus rq, module the relation given by the fact that the Chern polynomial of the tautological Chern polynomial of the quotient gives the identity, the product gives the identity. But there is the most interesting presentation, in my opinion, is the one that I saw for the first time in the papers of Witten. And only I saw, I saw Witten. I didn't see any paper by Witten where he doesn't use this presentation. And I saw also a paper by Bertrand where the presentation is this. X1, we are in the Grassmannian GRN, is X1, X2, I mean, XR, but there are infinitely many R, and dxn plus 1 equal to 0. This is another representation of the cohomology ring of the Grassmannian. And why this is, from my point of view, is the most interesting is because for elementary linear algebra consideration, this ring is isomorphic to this vector space, wedge RQN. There is this isomorphism. Okay, because if you can think, see, the cohomology is generated by the class of Schubert varieties, and the class of Schubert varieties are n over R, the dimension. For dimension reason are the same. But what is nice is that BRN acts on, of course, acts on the cohomology, which is isomorphic for dimension reason for Qn. And then you may wonder, what is this identification? This identification omega lambda to well, I can write BR minus 1 plus lambda 1. The obvious basis element of the exterior power associated to the partition lambda. Okay, so it's very natural identification. I don't want to spend more time on this, but the xi leaving here the same Witten use acts on wedge RQN as a derivation. I mean, is a derivation, xi is a derivation of the exterior algebra, meaning that if you do xi B alpha wedge B beta, you have xi B alpha wedge B beta plus B alpha wedge xi B beta. Then you may wonder what is this xi, but here I have an identification of this ring by means of polynomials in that ring B, and then, well, this is what I wanted to say, modulo questions.
Okay. So, Letterio, this is the end of your talk. Okay, oh, good.
Yes.
Okay. So thank you very much for your very nice talk. And is there any question or remark?
I already asked one question. So, but Letterio, thank you for your very interesting talk, very clear and very nice algebraic construction. So, Witten's description, well, at the end of the story, is related to the fact that you characterize the homology ring in terms of the homology rings of the universal Grassmannian.
Yes, for sure, for sure. This is, but I was thinking to that paper entitled, well, the title, the homology ring of the Grassmannian, and is a, I don't know even if it has ever been published, because I have a preprint form. Let me see.
Well, I don't know Witten's paper.
Well, I can give you the reference, but it's a very ancient paper. It's one of the first papers. If I think 5 minutes, it comes to my mind. But there was what is, is the quantum homology of the Grassmannian. He wanted to study the quantum homology of the Grassmannian. So to study the quantum deformation of the Grassmannian, he considered the presentation of the Grassmannian I showed to you now. That presentation is the most interesting, because if you use the Xi as generator of the homology ring, they act on the homology in a very easy way, because once you identify the homology as an exterior power, the Xi acts as a derivation of the exterior algebra. So it is sufficient to know the action of the Xi on the first degree of the exterior algebra, and then you know to all the Grassmannian. And then he constructed the quantum homology by subtracting Q.
Okay.
But I don't know if I answered to your question. Yes, but everything is universal there. Maybe I should say about the motivation. I couldn't say, you know, the point is that we have the intersection theory of modular space of curves, stable intersection theory of modular space of curves, the celebrated Witten paper where he compute a generating function of the tau classes, right? And then I asked myself, but why this kind of game has never been played in case of Grassmannians, which are the easiest example of projective varieties with a good intersection theory. And then I thought, how could I construct a generating function of some monomial like this? Okay, so what number I can associate to this? And you get a log immediately in trouble, because if you consider sigma 1,4 in the Grassmannian G24 is equal to 2, but the sigma 1,4 in the Grassmannian, in P3, not in G1 P3, but in G0 P3 is 1. So you have to give, you need to give a meaning to this expression, and it is possible. You can find what I call a Schubert calculus on the fermionic Fock space. You can find number. As a matter of fact, with respect to the definition I am not giving you, you can find that this is n factorial. And using this computation, you can find degrees of Schubert varieties, and you can find also a generating function of the integrals. And what is interesting, but even if it may seem trivial, is that the generating function of all these integrals satisfy the KP hierarchy, because it is expressed by means of sure polynomials, and sure polynomials trivially are solution of the KP hierarchy. But all this story I didn't tell to you. I wanted just to say these things that it surprised me. I mean, ingenuously surprised me that when you take derivatives of the Wronskian in the usual sense, all the coefficients are degree of Schubert varieties.
So we are back to integral systems.
Yeah, but you see, I mean, take a determinant, you take differential, you have a linear combination, you have the coefficients are all and only degree of Schubert varieties. This is the small thing I wanted to give you as a present, modest, but with by heart.
Thank you, Letterio. Thank you. I have to think about that.
Okay.
I want to read your paper.
Okay. Is there any other? Oh, sorry.
No, I'm just saying that unfortunately I cannot stay to follow the next talk because I'm in the middle of the international school.
Yeah, but at least for the picture you can stay.
Yeah. Let's do the picture.